engineering is at its best when it's learning from science. Now, data science, like every other science, has led to really powerful discoveries. In particular, in this case, these have been around how to model and represent very complex data so that algorithms can make better sense of the world around them. Now, it turns out that the state of the art in this today is something called attention. This is what's used in the transformer models that we have today. These are the algorithms that build up our systems like ChatGPT. And the basic idea here is to model how every data essentially attends to every other data. So the way that this works is, for example, the meaning of that sentence over there is encoded in how every word, which we loosely correspond in these algorithms to something called tokens, attends to every other word in the sentence. And that's captured in that relationship matrix. Now, this ends up being an extremely powerful algorithmic representation, but you can see quite visually from this matrix that it also has quadratic complexity. Now, it turns out, though, the interesting thing about attention is that this matrix is meant to capture a rich diversity of different relationships. In particular, that specifically bring out the most meaningful and the strongest attention patterns that we have in our data. And so it turns out to do that, this representation is typically sparse. That's how we capture these strongest attention relationships. This, in fact, works. We see this in practice, as I've shown over there at the bottom. And it turns out that this is actually being exploited to reduce algorithmic complexity through machine learning concepts like sparse attention. Now, the interesting question for us as we try to build sensing systems of the future is how can we take advantage of this sparsity up front, right at the sensors, so that we can improve the efficiency and the scalability of the systems that we build. Now, this sounds very reasonable. Of course, the challenge is that to take advantage of this up front, we need to know or learn these attention relationships even before the algorithmic relationship has had the chance to figure them out. So how are we to gain or learn this knowledge? What is it about the world that we might know that we could take advantage of? Well, it turns out, as all of you know, the world is an extremely complicated place. But it turns out it also has very rich structure in all sorts of different ways. And one example that I'm showing over here is that if you have a complex environment, like a command unit, or even a complex environment like a household kitchen, if we're engaged in complex tasks in that environment, we, of course, interact with characteristic objects. And that leaves embedded signals around those objects that are very telling of the complex tasks we're performing and maybe even the intentions that we have. And so it turns out that we've long been interested in embedded sensing because it gives us new modalities, because it gives us higher sensitivity. But it actually turns out that embedded sensors, by directly and invariantly associating the embedded signals with these characteristic objects and interactions, can also help us preserve structure of the real world. And it turns out that this also works. So over there at the bottom, I've shown a class of perception models for sensor fusion that explicitly take the structure that we get from these embedded sensors and that collate that on top of the representations, the feature representations that we have, for example, from remote sensors like imagers that don't necessarily preserve that structure. And so thinking in this way, it turns out that embedded sensing can help us close the loop. On the one hand, these structure-enhanced representations can improve perception. On the other hand, the structure in these representations can also help us drive algorithms for very selective, attention-selective sensor acquisition to improve the efficiency through that sparsity. Now, of course, the other component here is that we now need agile technologies for algorithmic sensing. And of course, new motivations call for new kinds of technologies. And one example over here is a reconfigurable antenna that's built out of a technology called large area electronics. Large area electronics is the same technology that we use to build very big solar cells or to build these flat panel displays. These have arrays of transistors to control each of the pixels. And it turns out that this is fabricated today on substrates that can be flexible and reach 10 square meters in size. These very large dimensions mean that we can now, with these very large radiating apertures, have extreme control over the radiation patterns that we can synthesize. And that's done here by controlling switches in between an array of patch antennas. Turning these on and off changes the surface current distribution and gives us these new radiation patterns. This works, and in fact, what we've also been able to do is build models, in this case based on graph neural networks that capture the physics of this sort of a structure, to solve the inverse problem that tells us how to set this high-dimensional array of switch configurations to get the radiation patterns that we want. And so I believe that sensing technologies of the future are going to take advantage of the deep insights that we get from data science regarding what the most powerful representations are, but then also exploit those to gain efficiencies like sparsity, together with sensing technologies that'll help us do algorithmic sensing in ways that take advantage of and realize those system efficiencies. Thank you very much.